Hi everyone. In this video, we will talk about the electric vehicle motor control systems as they are crucial for efficient, smooth and responsive operation. They manage the motor speed, torque and power consumption which directly affects the performance, range and reliability. So therefore, it is very imperative to understand what are the motor control systems, techniques are available, what are the components are required, and how to perform all these motor control systems for the better driving efficiency. So let's begin. So let's begin with the what are the motors being deployed or being used in the electric vehicles. So we have already seen in our previous videos that mostly four types of the motors are very popular for EV applications, and those motors are number one is the PMSM, or the permanent magnet synchronous motor, which is known for its high efficiency and torque density, and the very versatile motor, which is the induction motor, which is being used in the earlier versions of the EV like Tesla models, and they are popular for their robustness and for the lower cost. And the third is the switched reluctance motor, and also abbreviated as the SRM, which is known for its simplicity, durability, and however they tend to be a little bit noisy. And the BLDC motor, which is commonly used in the electric two-wheelers like electric bikes and electrical scooters. So therefore uh, they have these smaller EVs, they have been used for the smaller EVs for their efficiency and ease of control. So these are the four motors which is popular in the EV application as per the current trends, and all these four motors requires different control techniques due to their unique electrical and magnetic characteristics. Like a BLDC motor has the two types of the rotor, which is outrunner and inrunner, and they also have can be of type of the permanent magnets. Similarly, permanent magnet synchronous motor PMS motor also has the permanent magnet rotors. However, the induction motor are again two types. One is the squirrel cage, and the other one is the slip ring, and they do not use the any kind of a permanent magnet features. So therefore, all these four motors are the different in their uh, characteristics, different in the build, different in their operations. Therefore, all these four motors are required the different control techniques. So let's uh, talk about the control techniques which is available to us as of now, and how to deploy all those control techniques in the EVs through the components. So the motor control systems in EV involves the power electronics, usually in the form of an inverter, and they can be of the open loop control techniques or the closed loop control techniques, which uses the sensors and the software algorithms to implement it. Uh, the number one control technique is the, or I can say that it is the simplest control technique, which is the V by F control, which is also known as my uh, scalar control. So mostly we have two types of broadly we have the two types of the control techniques. One which is fall under the category of the scalar control, other one which is fall under the category of the vector control. So therefore V by F comes under the scalar control. It is the simplest, easiest control technique which is being implemented or can be implemented. uh, it controls the speed by adjusting the voltage and frequency in the fixed ratio, maintaining the magnetic flux, air gap flux, and it is mostly being used in the induction motor. It is, as I've said, it is very simple, inexpensive because it does not require the sensor feedback or very complex circuitry. So therefore, it is simple and inexpensive, and it is being used where the precise torque control is not required or needed. So therefore, applications something like that fan or pump or a small kind of application where the dynamic changes or the precise changes are not required, there it is being implemented. It has a limitation, as I've said, that it is a scalar technique. So therefore, it lacks in the precision in the torque control, and it is unsuitable for the high performance EV applications. So it is not being used in the EV applications. Uh, However, it has the application such as pumps or fans or within the vehicles, which is being used in within this vehicle. So therefore, there we can implement the V by F control as an auxiliary systems. And the second control technique is the field-oriented control, which is also known as or also fall under the category of the vector control. It controls the motor magnetic flux and the torque independently. So this is the beauty of this control technique, that it controls the magnetic flux independently and the torque independently, similar to my separately excited DC motor. If we can recall that separately excited DC motor has two independent circuit. One is the armature circuit, which is basically for the torque, and the other one is my field circuit, which is again given supply separately. So simple here. DC motor, which is separately excited DC motor, is very easy to control because it has the two separate circuits. So the torque and the flux can be controlled independently. Similarly, if I want to have the control, let's say in case of the PMSM motor or the induction motor, I want to have this such kind of a control where I can independently control the torque and the flux. So there FOC comes into the picture, which is very handy to give me such kind of a control. Advantage, it has a precise control over the torque and the speed. It gives me the smooth operation across a wide speed range. However, it has the limitation in terms of the higher computational complexity and require very powerful microcontrollers. But as now we are evolved with the very fast responsive microcontrollers, so this it does not have any implication on my EV performance. Applications are used in PMSM, induction motor, and high performance EVs due to its responsiveness and the efficiency. And I would say that FOC is nowadays being implemented in the EVs. Though we have one more control technique which is also being deployed in the EVs, which is the direct torque control. So here, so direct torque control, uh, it directly controls my motor torque by adjusting the stator flux. So it directly controls the torque by adjusting the stator flux and selecting the appropriate inverter states. So as I've stated earlier also in this video, that the motor control system heavily depends on the power electronics. And here the inverter we are talking about, which is being deployed in the EVs over here, mostly controlled with the help of the pulse width modulation. And to do so, how to give the switching signals to my inverter, which is being operated on the PWM concept. So that is being done through the direct torque control, which is further controls my motor. So here, let's say if my motor is over here. So how to operate efficiently the inverter which can control the motor, because the motor taking input from my inverter itself. So therefore, the control techniques operates my inverter efficiently, and inverter in turns operate my motor speed control and the torque control also. And the main advantages of that, it works without transformation. Transformation here, guys, I'll just give you one brief over here. Although we'll talk about this in brief in other lectures or in other videos. The transformation, like in FOC, which we have just seen, the FOC involves the transformation. What kind of a transformation? Because here we are talking about the three-phase AC motor which is being deployed in the EVs. So this three-phase value, which is for the stator reference frame and the rotor reference frame, has to transform by some mean so that I can have the control such like a DC motor, DC separate excited DC motors. So therefore, the FOC involves, one is the class transformation, and then it also involves, after the class transformation, it also involves the parts transformation. All these transformations we will talk in the brief in separate video, which is nothing but the kind of a mathematical modeling. What it does, it creates the three-phase, from the three-phase it creates the two coordinates in terms of the alpha and beta. So Clark transformation does that, and the alpha beta again further decoupled in form of the two time invariant coordinates, which is the DQA, also known as the direct and quadrature axis. So this is happens in the FOC control, or the field oriented control, whereas such kind of a transformation is absent in the direct or control, so that making it more faster than the FOC. Advantage, as we have already stated, that it has a fast response, high torque accuracy, and simple control structure, because it does not involve such kind of a transformation. So therefore, it has the simple control structure as compared to my FOC. However, it do have some limitations, that it is prone to torque ripple at low speed and require high speed switching, which can lead to heating. So therefore, in case of the DTC, thermal management comes into the picture, which we have to better manage in EV. So because due to the high switching, it will create the more heat over here, over the inverters. Therefore, it requires better thermal management. So it requires better thermal management. Applications, it is used in the induction motor, some of the PMSM motor, in EVs where quick torque response is critical. The one more kind of a motor control techniques, which is, I would say, the kind of advanced technique, is known as the model predictive control. What it does, it uses a model of the motor itself to predict the future. So let's say if some performance has been occurred, or some my motor is performed on some certain scenario. So what it does, it will for the future it will ready for the such kind of a cases. So therefore it can predict that this kind of a situation is going to come, and in the previous case how the overall system has worked. So therefore it trained itself, and then it can be ready for the future if these again the same kind of a problems occurs. So therefore it uses the model of the motor to predict the future behavior and adjusts control signals to optimize performance. So therefore it is implemented kind of in the real time or the rapid adjustment. Advantage, it has high efficiency, high performance, and adaptable to varying load conditions, which is kind of a very handy for EV applications. If I have such kind of a EV which is adaptable to my varying load conditions, I'm going uphill, I'm going downhill, I'm going off-roading, something like that, and all these three conditions, if I'm getting the better performance or the let's optimize performance from my motor, so definitely it is going to increase my EV range and its durability. So therefore I would say the MPC going to be sometime in going to be the future control techniques in case of EV motor control system. However, it does have the limitation that it has the high computational demand and require fast processor. Application suitable for next generation EVs where predictive control helps in optimizing energy efficiency and driving dynamics. And I would say I would add one more point over here, that MPC again will be more beneficial and more efficient for autonomous vehicle, where we will have the more adaptable EVs, we will have varying load conditions, we will have the uncertain environment, and we have to take the very fast response. So therefore MPC definitely will support my autonomous vehicle. And the last control technique which I will give brief over here, that is the hysteresis control. which works on the control current, which controls the current and the voltage within a defined range, also known as the hysteresis band, to achieve the desired motor performance. It is very simple, robust, and fast response. However, it results in the higher switching frequency, causing increased heat in the motor and the power electronics. So again, the same point comes that we need a better thermal management. However, it is less common in the modern EVs, but can be used in the motor drivers requiring rapid torque response, particularly at low speed. Again, to implement all the control algorithms which we have just seen, we need the components for the EV motor control. And the most important, I would say, the most important component in EV, that is the inverter. All the control is happening through my inverter. And as I've stated, that all the modern inverters uses the pulse width modulation to precisely control voltage and current of my motor input. The other is the motor controller, and this is also called as the brain of the motor control system, which uses a software algorithm to interpret the driver's behavior or input and manage the inverter to achieve desired speed and torque. So all these things happens in the closed loop control system. We do require some sensors to have the precise control over my motor. Uh, these sensors are the position sensor, also known as the encoders, which is being used in the FOC and the DTC systems to provide real-time rotor position feedback for accurate control. So the FOC and the DTC systems are the sensor-based control techniques, whereas my V/F control is the without sensor-based control techniques. The other sensor is a current sensor, which measures the motor phase current for torque and the flux control, and the temperature sensors, which monitors the motor and the inverter temperatures to prevent overheating or to provide my better thermal management. If we have to compare the V/F control versus the FOC control and the DTC control, so in the control approach, as I've stated earlier, that V/F is the open loop control, which manages the voltage and frequency. FOC is the vector-based control, which works on the DQ axis or the DQ component, and the DTC direct control of my torque and the flux. Torque response, in case of the V/F, it is low, I would say imprecise. FOC gives very high precision, and DTC gives very fast because it does not involve the transformation, as in the case of the FOC. Efficiency, V/F have the lower frequency as compared to my FOC and DTC. So amongst all these three, FOC has the highest efficiency. In terms of the complexity, V/F is very simple. FOC is complex because it requires a transformation. It requires all the microcontroller taking actions, whereas the DTC is the less complex as compared to FOC because it does not involve the transformation. Application wise, V/F has the low cost, low performance EVs applications. FOC is being used in the high performance EVs applications. Again, the DTC also being used in the high performance EV applications. The motors where it is being implemented, V/F implemented mostly or primarily in the induction motor, whereas the FOC is being implemented in the PMSM and the induction motor. And the PMSM is nowadays being deployed in all the EVs model. And the DTC is again used in the induction motor. So the challenges in EV motor controls are that one is the energy efficiency, that high efficiency is critical to maximize range. So therefore, motor control must minimize losses in both motor and inverter. Thermal management, because we are very frequently talking about the thermal management, due to the high switching happening over the in the inverter or the power electronics devices due to the FOC and DTC implementation, it requires a better thermal management. Smooth operation to ensure the smooth torque production, especially at the low speed, just to avoid the jerks, and the enhanced drivability. In terms of the cost and the complexity, advanced control techniques require powerful process and sensors, increasing the cost and the design complexity of the system. So in this video, we have seen all the motor control algorithms, their components, what are their roles, how one FOC leads by all the other control algorithms. So therefore, in EVs, motor control systems play a critical role in balancing performance, efficiency, and cost. V-by-F control is simple and affordable but lacks the precision, while FOC and DTC offer high performance and are used in the advanced electric vehicles, where precision torque control is essential. So as EV technology evolves, more advanced control techniques like we have seen the model predictive control or MPC may become the standard, and it will also help us further to develop the autonomous electric vehicles, optimizing energy efficiency and improving the overall driving experience. Thank you.